Go.
It's on? Oh, okay. So we got all the numbers outside, and we're too cold to stay outside and actual videotape there. So we have this small scale model that we made inside. Well, we'll be explaining what we did. The speed limit is 20 where we did it, because we didn't do it at a stop sign. But it's inconvenient to do it at a stoplight, because then you have to like go around. But if you're just on a regular street, you can stop and just back up and just keep doing it. And we went up to 30 miles an hour, so we're kind of living on the edge. But no cops are around. So it's
Ebola.
it's good.
Are you recording?
So yeah, that's our intro.
I'm eating a salad.
You can cut it now.
This is going to be a demonstration of what we did with the real car outside. So we marked a certain point on the street and we backed up the car and we had it accelerate at to a certain speed, and once it passed the spot at a certain time, we applied the brakes and we measured the distance from how far the car went after it stopped after we applied the brakes.
Alright, so our acceleration is going to be from the point where we start braking. So we first, with the demo she did, we got up to because we did them in miles per hour from 10 to 30. So for 30 miles, for example, before we brake, you have to get up to 30. But if you're doing the acceleration of the whole thing, it's not going to be accurate. So your initial would be 30 miles an hour, and that's when you start braking, when you pass that line. So you find the negative acceleration from when you start braking to when you stop. And then with so that's how you find the acceleration. And then for the specific distance, since technically in the real world you can be an inch past the stoplight line and you can still be fine. And sometimes I've seen like a full car length brake past it. And then but we're gonna assume that you legally have to be behind the line or else you'll get arrested. You know, that never happens. At least you try to brake, it's fine. So we're just going to assume that the specific distance from the intersection when you have to brake by is going to be directly behind it. So if you're going 30 miles an hour at the intersection, which is the one we went to, well, we didn't go to, but it exists. We found that in order to safely brake right before the line, you have to brake by 24.92 feet away from the intersection. So if you go at 24.9 feet, you're gonna go past the line. But if you brake before it, you'll be fine. So Ahmed, if you knock that over. Yeah. So Ahmed brakes. Let's see. That's about 24. So if he brakes at 24, it'll stop there. But if he brakes at, say, here, he'll go here, and then Johnny will hit him, and alright. Okay, so continuing from last time, that explosion thing with Ahmed and friends only happened if you brake after the 24.92. So so this is like the 24.92. If you're already passing, you have to brake. It's a lot safer just to go here. So like, because if you stop, you'll. But if you keep going, you'll just get chinked on the back, and no one will die. So we'll talk about the coefficient of friction stuff.
Okay, so we googled the coefficient of friction for rubber on dry asphalt, and it was 0.9, and our average was 0.931, but it fluctuated a lot because there's a lot of room for timing errors, like Abraham's going to tell you.
Alright, so it's pretty hard to tell the time, because if you take a video of it, you have no idea when the driver's hitting the brake. You can have someone drop his hand or tell the driver to brake, but the driver has to react to him, and the person saying that stuff has to react to when he comes, so it's there. The person inside the car has to react the same way. She's timing, and then he determines when the car's gonna rock. Person outside timing, he's reacting to someone telling them to start braking, and he's stopping the time when he sees the car rock back. The people inside the car may feel the car keep going. So it's pretty hard to determine a time. So you have to take a time in like every single way and just find the best one. Was taking the time from inside the car based on someone outside telling us when to brake.
Just like the coefficient of friction, the acceleration fluctuated as well as a result of the time, but in the end, the average acceleration was negative 9.116 meters per second squared.
We're going to talk about the three graphs now. We did velocity versus distance, which is how fast you're going versus how far you go after you brake. The second one is velocity versus time, which is how fast you go, how fast you're going versus how long it takes to brake. And the third one is distance versus time, which is how long you move after you brake.
Alright, so to recap of all of our data, so it's all in one spot. Just fast forward back to that. Our acceleration of the vehicle, well, all this data is going to be based off of going 30 miles an hour. We did other speed limits to get graphs. So our acceleration at 30 miles an hour after braking is negative 9.116 meters per second squared. Our specific distance from the intersection at which the car can no longer brake is anything after the 24.92 feet, which is where you get that explosion. Our coefficient of friction for the tires is 0.931. Our local speed limit was 20, but we went 30 to simulate the stoplight, because that's what if it was 30 at the stoplight. The minimal safest distance is 24.92, because as I said earlier, anything after that you'll get into the intersection. The zone in which the car must accelerate through the intersection, even if it changes colors, is the same thing as the unsafe after braking, and after 24.92, just keep going. And then, yeah, we're going to put a table and our graphs after this, and then that's our red light experiment.